All right, let's start lecture 2 by returning to electromagnetic radiation, because what we will see here is that electromagnetic radiation was the probe that scientists used to unravel the structure of atoms and molecules. Of course, we don't have powerful enough microscopes, if you like, to see individual atoms or molecules, so there was really not much understanding as to how atoms and molecules were actually designed. So what was done was that light, with as scientists shined light on atoms, the light underwent characteristic changes or disappearances, or interacted with the material in the samples to such an extent that they could make connections to what happened to the light, and from that information figure out what type of structure the atoms and molecules must possess. So if we for a moment think about Rutherford's planetary model, which we're going to go away from, but we'll hold on to it for a few more moments here, and we will think about the electrons as moving like satellites around a planet, and as they move around as satellites around that planet, they are charges in motion, and so charge in motion creates an electric field. Well, then if you shine light on the particles of this atom, the light wavelength has a certain size to it, and we'll just begin by saying we might have light of any wavelength. We send that light on to the atom, and most of the various wavelengths of light corresponding to various portions of the electromagnetic spectrum, so like radio and microwave and many others like X-rays and on, we can think of them. Well, they will have no interaction because their fields are so out of phase with the motion of the field that is generated by the motion of the electron around the atom. But if you tune into just the right wavelengths, between 400 and actually even down lower than that, I would say between 300 and 700 nanometers, mostly a little bit in the UV, but mostly in the visible, what we will find is that the light is now of just the right frequency to interact with the electrons in motion around the nucleus. You can think of it like your kid sister on a swing. She is at zero energy when no one is pushing on her, and she sits motionless on the swing. But now as you begin to push her, you can put her into an excited state. Now, provided that you apply a push at just the right frequency, you can keep her maintaining that excited state. So this is much the same as we can think of which happens with an electron going around a nucleus. Light of just the right frequency hits the electron every time it comes back around and stimulates that electron perfectly so that it's maintaining a higher energy state. Of course, while this is going on, the light is losing energy. Energy is transferred from the light to the electron moving around the nucleus. So there will be a deficit of energy in the light as this occurs. So we have fancy techniques to measure that. Light of a certain energy or brightness comes in. Then if the particular material in the sample likes certain wavelengths of the light, they interact with the electrons, and the electrons steal the energy of that light, putting the electrons into higher energy states, but removing that energy from the light. So the emerging light, we check to see what wavelength, at each wavelength, what type of energy loss the electromagnetic radiation of that wavelength has experienced, to give us information about what kind of light is absorbed by the atoms. Typically, atoms with their electrons in motion around them love ultraviolet or visible light of wavelength between 300 to 700 nanometers. Actually, I said they're a little lower than that even. And so we can look and use this probe to understand, or at least gain some information about the atoms themselves. So, when we have atoms at low energy and we put light of the correct frequency or wavelength, we shine the right wavelength of light on it that can interact with the electrons, it can impart energy into those wavelengths, and those atoms can absorb that energy from the light and stimulate the electrons to higher energy positions. They will maintain those higher energy positions as long as the light stays shining on the atoms. And this is kind of like your kid sister stays swinging at a high energy state as long as you keep pushing at just the right frequency to stimulate her into that high energy state. Now, not only is light absorbed to send electrons to their higher energy states, light is emitted when electrons in atoms cascade back to their original low energy state. So there are other mechanisms by which we can stimulate the electrons in atoms other than light. For instance, two obvious ones that you can encounter all the time are electrical stimulation or fire stimulation. In electrical stimulation, like when we plug in a light bulb, electrical current goes through atoms in the tungsten filament of light. The electricity is absorbed by the atoms this time, exciting the electrons in the atoms. And as these atoms cascade back to where their electrons want to be in energy, they have to shed the energy. They can't just sweep it under the rug of the universe. So they spit the energy out in the form of electromagnetic radiation. So as the excited atoms, electrons, return back to where they would prefer to spend most of their time, they have to shed the energy, and they shed it in the form of electromagnetic radiation. Now in the fire case, for instance, when we see we have a fire burning and we see all this yellow flames coming off the fire, that's an indication that the carbon atoms in the fire have had their atoms of each atom, not each, but most of their atoms have been excited in the electronic sense. The energy of that fire is enough to send electrons to higher energy states. But now as the atoms return to their original energy state, they have to shed that energy, and they shed it in yellow light. So we have emission of light when energetically excited atoms that can be stimulated again in other fashions than just light itself. When they emit their light, we detect it. Now, depending on the type of atom, we will see the wavelengths of light emitted as the electrons cascade back to their original positions. We'll see different amounts of energy emitted because of the structure of the atom. And then so there will be different wavelengths of light characteristic to the atom itself. Now let's recall, as we do at the bottom there, that the energy of light is inversely proportional to this wavelength. In the visible range, the low energy light is the long wavelength light. That would be the red end of the visible spectrum. Below that would be the infrared, that would be even lower energy. And then as you go to high energy light, it's the shorter wavelength, violet end of the electromagnetic spectrum of the visible light. If you go to higher energy, you go into ultraviolet. So different atoms, again, will prefer to emit different of these wavelengths of light. So they might give off purple, some might give off yellow, some might give off red, depending on the difference in energy between the level of their ground state and their excited state. This slide kind of summarizes for you the emission of light that atoms undertake when they are stimulated energetically and their electrons gain extra energy from their normal states of energy. And as those stimulated electrons attempt to return to their original spots, they have to shed that energy, and they do so in the form of light. So we talked on the last slide about light being, or atoms being stimulated electrically or by fire. Here, what I will say is in a chemical explosion, the energy of the chemistry of the process of a very rapid occurring chemical reaction, which we call an explosion. During the explosion, a huge amount of energy is transferred to atoms that are packed in among the explosives. And so these atoms get stimulated by the energy that is released during that explosion. This stimulates the electrons to high energy positions. They want to shed that energy to return to their lower energy positions, and they emit light as a result of this. So the emission of light comes about from these atoms that are stimulated due to some external energy source, giving them the energy that they can emit. Now, the higher energy emissions, the further the electrons have to hop to return from the energetically excited state back to their original state. That will correspond to shorter wavelengths of light. So if these atoms have particularly big gaps between their states of energy for the electrons when they start to where they end up, then that will take a lot of light energy to be emitted when they cascade back to where they want to be, the electrons. So that means it will be emitting the blues and the purples. If it's a relatively small amount of energy to be emitted by the electron to return to its original spot, then it will be a red or an orange or a yellow light that will be emitted. So the color of the firework will depend on the type of atom, and what happens in the type of atom is that characteristically has a certain amount of energy between the positions of the electrons in their high energy state compared to their low energy state. Now, interestingly, all atoms of the same type will have the same characteristic distance between these energy levels, so they all will emit these same kinds of light. They all will absorb. It can go the other way as well. If I shine light on them, they will absorb light of the characteristic frequency. All hydrogens absorb light of the same characteristic wavelength or frequency. All oxygen atoms absorb light of the same characteristic frequency. All iron atoms absorb light of the same characteristic frequency. So, shining light of a particular frequency that you know a particular atom likes onto the sample, you can tell if the sample is present and actually how much of that sample is present. You can tell how much it is present because the more atoms of that type that are present, the more of this particular wavelength of light that this sample will absorb. So you can measure, it starts out as a really bright light, the more of these particular atoms present will dim that light, and the dimmer the light gets as it emerges tells you quantitatively how many of the atoms of that type were in that sample doing that absorbing. So not only do we know qualitatively what type of atom is present based on the emitted or absorbed light that they prefer, we also can tell how many are present by the brightness of the emitted light or the dimness of the leftover absorbed light that comes through the sample. Some of the familiar sources of white light that we have around are, of course, the sun. The sun is it does this in the cataclysmic action of the fusion of hydrogen to form helium, and two heliums connecting together to make a beryllium and a helium hooking together to make a carbon. This is called nuclear fusion. So the sun carries off nuclear fusion, and during the course of jamming nuclei together, huge amounts of energy are emitted. These huge amounts of energy that is emitted stimulate all sorts of a wide variety of excited state electrons, all then cascading backward to their lower energy positions to give off basically the entire electromagnetic spectrum of frequencies of light. So all wavelengths are emitted, and including radio waves and microwaves and infrared and ultraviolet. All these things are being emitted, and as well as, of course, visible light. So the visible light of all red, orange, yellow, blue, green, violet wavelengths that are emitted combine together, and the combination of all visible lights is white light. So the sun is about a perfect white light source due to the stimulated emission of the very many huge amount of varying electronic excitations and other processes that go on the sun to send that light beaming to us. Now, humans have come up with their own white light sources. Of course, fires, for instance, seem to give off yellow light, and that again is familiarly due to fire sources of fuel being mainly carbon sources, and it's the carbon in those sources that is emitting the yellow light when the electrons in the carbon atoms cascade characteristically back to their low energy positions. Now, light bulbs come in two forms. The older ones are the incandescents, invented by Thomas Edison. They take a current of electricity, send it through a thin filament of tungsten. Turns out tungsten atoms are really good at emitting not only one color of light, but pretty much the red, orange, yellow, blue, green, violet parts of the spectrum pretty much equally. So mixed together, incandescent lights make pretty good white light sources. Now LEDs, and I'm sure you've been able to discern that if you've used LED light bulbs recently, they use diodes, and the diodes can be tuned to their emissions so that diodes of several different types that emit red light, blue light, green, orange, yellow, all those different colors, they can be put together collectively to make nice, clean white light. You might notice that light bulbs using LEDs are really bright and seem to make things pop and stand out because they are really good white light sources. Now, fluorescents, on the other hand, are not nearly as good of a white light source as either incandescent or LEDs. LEDs are just a recent addition to our repertoire. We didn't know how to make them several years ago, but it's been quite a while. We've known how to make fluorescents for quite some time. And fluorescents have certain advantages over incandescents. The main one being is that incandescents, in addition to the light energy they give off a huge amount of heat energy. That's why an easy bake oven has a light bulb in it. Fluorescents warm up when they are emitting light, but they don't give off near the level of heat energy that incandescents do. So if large rooms, if factories and stores and classrooms were all heated with incandescent bulbs, there'd be a huge amount of heat energy being dumped in the room. The rooms would be incredibly hot. So fluorescent lights can generate light with much less heat energy being dissipated along with the light energy. Now the problem first of all, the fluorescents do so by sending light through a tube full of mercury vapor. The mercury vapor stimulates what is known as a phosphor that coats the inside of the tube, and it's the phosphor in the inside of the tube that ends up emitting the colors of the visible spectrum that you see for the fluorescent. But the fluorescent is not nearly as clean of a white light source as LEDs, and not even as clean as a white light source as incandescence. I think we're all familiar with the fact that that fluorescent lights make you look a little pallid. They don't make you look nice and bright and pop when you're in the fluorescent light. But the advantage of the lack of heat that is generated when fluorescent light bulbs are used make them much more prevalent in large industrial settings, big classrooms, and things of that sort than incandescent bulbs. What I will tell you, though, without question, is that what we have discovered now with the advent of LED bulbs, they are clean sources of light, low energy sources of light, and also do not give off heat like incandescents. So I predict that in a very short amount of time, fluorescent bulbs are going to completely go away. All bulbs will be LED bulbs, and you'll even notice that they have designed LED bulbs to fit in the fluorescent fixtures. You don't even need to put fluorescent light bulbs in the many fluorescent fixtures that are all over the country. They can put LED bulbs into those fluorescent fixtures now. Let's say a little bit about light reflection as opposed to light emission. Anything that you energetically use as a light source is emitting light, like a fire emits light because the chemical reaction of the fire stimulates the emission of electromagnetic radiation. Light bulbs emit light. You plug them into a source of electrical energy and they spit light out. Explosions emit light because of the chemical energy that is generated during the course of the explosion, stimulates the emission of electromagnetic radiation. Other things like a t-shirt or a painted wall, these are not light emitters. That's not the proper way to use the terminology. A painted wall is a light reflector. A t-shirt is a light reflector. Anything that doesn't glow in the dark can reflect light, but it can't emit light. Okay, so we will save emitted light for the energetically stimulated light that is passed from an object. Other things must reflect light. And as a matter of fact, if you turn the lights off, there's nothing for them to reflect. You can't even see them. So let's now think of a blue t-shirt. It is reflecting blue light. What that means is from the white light source, whether it's the sun or whether it's a light bulb in a room or whatever it happens to be, all colors are impinging on the shirt from that source. Red, orange, yellow, green, blue, violet. But now when the light bounces off of there, it comes to your eyes, you see blue. So you see from all white light impinging, you see blue light reflecting. Now what we will take into account is that the primary colors from which all others can be made are red, yellow, and blue. So if red, yellow, and blue light are striking the object, but only blue light is emerging, that means that the object is removing the red and yellow light. Now where did it go? It didn't disappear under the rug of the universe. The red and yellow light is being absorbed by the dye molecules in the t-shirt, and what it's doing as it's absorbed by the dye molecules in the t-shirt is stimulating the electrons in the dye molecules to higher energy positions. As long as the white light strikes the t-shirt, it will absorb the red and yellow light, stimulating its electrons, keeping them swinging. Remember what I said before, like your kid's sister, she won't stay up in the higher swing energy levels unless you keep stimulating it. So the, the white light from the source impinging on this continually stimulates the electrons, and as that is done, the red and yellow light is absorbed and given to those electrons, so only the blue light remains to reflect to your eyes. In a similar fashion, if you look at a plant, you'll notice it has green leaves. Well, those leaves are not emitting light. Again, those leaves are reflecting light. White light is striking the leaf. It's a mixture of all colors, and most importantly, we'll say red, yellow, and blue. And when it reflects the light, only the yellow and blue or green light comes to you. That means that the plant, or the leaves of the plant, must be absorbing the complement to what you're seeing. The leaves of the plant are absorbing green light. What about when an object appears black? Well, black is the absence of color. So when white light impinges on a black t-shirt or black automobile paint job, black wall paint or something of that type, what is happening then is all visible portions of the electromagnetic spectrum are being absorbed. Where's that energy of that light going? Stimulating electrons in the dye molecules of the t-shirt, wall, or whatever. But now, since all visible wavelengths of light are being absorbed, there's none to be reflected. So in this instance, the object appears black. To summarize these concepts, energetically stimulated objects can emit light. They don't all have to, but they can possibly if the electrons in the atoms of that matter get stimulated, the electrons in that matter must return to their original spaces. They don't stay stimulated forever. And in the course of emitting the energy, the electrons in those atoms can emit visible light. Other objects that are not that you see and are giving off color and things like that may not be emitting light. More correctly, we should say they are reflecting light. And the way to tell the difference is if you turn all the lights off, can you still see any surrounding lights? Can you still see light coming from that object? If you turn all the lights off on the overhead, you'll still see a light bulb emitting light on a lamp in the room. But if you turn all the lights off overhead, you won't see the color of the wall anymore because it's not reflecting light that was emitted from the ceiling. Okay, so if the objects naturally, or if they contain dyes that absorb a portion of the white light spectrum, the complementary colors of the spectrum are reflected. So in other words, if it absorbs red, or if it looks green, that means it's sending the blue and yellow to you. It's absorbing red. If it looks purple, which is sending the reds and blues to you, it's absorbing the yellow. And if it looks black, it's absorbing all light. Now, white objects are actually reflecting all wavelengths of light. So an object which appears white, a white t-shirt, something of that type, is bouncing all colors that are reaching your eyes simultaneously, and they are combined to look white. So one of the questions that light emission of atoms caused was, why do atoms of some particular type only emit a certain color? Why don't they emit all colors? It seemed logical that, okay, we can think that these electrons are getting stimulated by the energy that you input into the atom, and now as the atom is trying to get back to where it was at the beginning, it's going to emit light to do that. But why would it emit light of only a certain frequency or wavelength? why not just emit all different kinds of light from that same atom? So this was a problem that bothered people, and it particularly bothered them when put into combination with what had recently been thought of at the beginning of the 1900s by Rutherford. If you recall, we talked in our last unit about the fact that when subatomic particles had been found by J.J. Thomson, he built a model of an atom to include the fact that it contained positive and negative charges by putting plums of electrons of negative charge into a pudding of positive charge. The reason he did that was he knew the positive charge was way more massive than the negative charge, so the negative charged electrons were like little plums in the big bowl of positive charge pudding. Well, when Rutherford did an experiment that showed he could shoot charged particles through the atoms, and sometimes they would bounce off, but mostly they would pass through, he decided an atom was mostly empty space. So much like our solar system, Rutherford proposed the planetary model of the atom, where the negatively charged smaller electrons orbit around the center massive positive charge in the nucleus. Again, if you recall, he also predicted the existence of neutrons in order to hold all the positive charge of the nucleus localized in the nucleus. Well, as scientists began to unravel Rutherford's planetary model, they also saw that it had problems. Electrons are charges, and charges which are moving circularly in orbit are actually accelerating. The only thing that keeps them in a circular motion is that something is dragging them inward. So something is pulling them into a circular motion. So a force is acting on the electrons, so therefore they are accelerating as they change direction as they move around the nucleus. If there was no force acting on them, they would just travel in a straight line. So the fact that they're moving in a circle means they must be experiencing a force that is accelerating them. Well, according to what physicists understood, any accelerating charge should give off radiation. So you should be able to find some frequency of light or wavelength of light being emitted by all electrons that are moving around the nucleus. So atoms, even when they are not energetically stimulated, should be emitting some form of light. Scientists went and looked for that form of light that they should be emitting and couldn't find anything like that, so they knew that that wasn't occurring. Well, even worse, accelerating atoms that are radiating, accelerating charges must radiate. Radiation causes you to lose energy. So what should happen as these electrons move around the nucleus and radiate is that they should decay in energy. When they lose their kinetic energy, according to 1 f(mv²), they slow down. When they slow down, the attraction they feel to the nucleus pulls them in closer. They can't maintain a stationary or an orbit of the same height, if you like. They're now being pulled inward more than they're being pushed sideways, so they start to come spiraling inward, and eventually these electrons should crash into the nucleus. So because the electron behavior was defying what should be happening according to how physics was understood, scientists said, well, there's something wrong here. Our physics is not fitting the situation of the way electrons move around the nucleus. We need a new model. So essentially what we're saying is the scientific method, evidence became available that violated the theory that had been proposed to explain the atom. A new theory was needed that could be tested to see if it fit the behavior of the electrons in motion around the atom. So when the failures of Rutherford's planetary model in physics came to light, scientists quickly looked for another model of the atom that could fit the observed evidence. The physics that was used describing Rutherford's planetary model was what we would now refer to as classical mechanics. It's the old way in which physicists interpreted the physical world. It was begun by Isaac Newton in the 1600s. It was enhanced by individuals like James Clerk Maxwell when they added the theory of electromagnetic radiation in the 1800s, and it lasted up until about 1920 when the problems arose in interpreting the behavior of Rutherford's model of the atom. It was understood that the rules by which we said matter worked were not working when we looked on the scale of matter at the level of atoms and molecules. So, in fact, not only does this so-called classical mechanics fail for atoms and molecules, as we see there on the right, it also fails for very massive systems, like huge events in the universe where stars collapse upon themselves, creating an incredibly dense state of matter known as the black hole. It's so dense that even it has such high gravitational effects that even light cannot travel out past or through these gravitational pools. And it pulls all the light out of space, creating a dark spot in space known as a black hole. It was also figured out, much of that was discovered by Einstein. Einstein also figured out that the rules of the Newtonian physics that had been established for hundreds of years also did not work when things start moving incredibly fast. We call that a relativistic correction that has to be made. As objects approach the speed of light, very bizarre things begin to happen, including objects becoming incredibly larger in size than they are at normal speeds. Objects become very massive when they move at incredible speeds. Well, actually, not objects become longer, it's just the distance becomes longer itself. And not only does distance change in dimension as things begin to move fast, that results in time spreading out. And the way time elapses in systems moving very quickly compared to the way time elapses in systems moving at normal speeds is quite different. So all of these events, some of them were predicted, and then scientists looked for evidence of them and found them. In particular, 2 and 3 were predicted occurrences by Einstein in particular, and then scientists went to look for evidence of them, and they found the evidence for them. The first one, the very small systems like atoms and molecules, disobeying classical mechanics, it was actually found experimentally, and then we had to design a new theory to fit the experimental mistakes that the old model of physics was trying to show how those things behaved. So, what is the gist of quantum mechanics? Well, what is the gist of classical mechanics? I kind of spilled the beans there on what we're going to change into. But the failing form of science essentially had a model of energy that says energy is continuous. Now, what does it mean that energy could be continuous? It means that energy can take all possible values. Now, this kind of makes sense if we think about maybe throwing a baseball. I can envision that I can throw that baseball at almost any, well, literally, technically, any speed I want. And I can, by just slightly varying the speed at which I put on the baseball, then by changing that speed into 1/2 mv squared, I can slightly change the energy of that baseball by any amount I want. Or the same thing with driving a car. I have the gas pedal that I push on and it changes the velocity of the car. In theory, I can push the gas pedal gradually to any degree that I desire and change the speed of the car gradually to any value I desire. So in this way, all possible energies seem to be likely. Now that's what is true in our macroscopic world that we live in. Huge entities like you and I seem to experience continuous states of energy, meaning I could go up and down an energy ramp by any amount I want. I can go up, which would be absorbing energy, and I could have an increase in energy as I absorb it of any fragment of any amount I want. I can go down in energy, down the energy ramp, and when I do that, I can go down by any amount I want, and giving off energy or going down in energy, I do so by emitting the energy. So when I'm in a high energy state, I emit it to go down the ramp. When I'm in a low energy state, I absorb it to go up the ramp. And according to the old ideas of Newton, I should be allowed to go up or down the ramp in any amount that I want. So what was developed in order to um, describe the disparities and problems that the old form of Newton's style of physics gave in interpreting the behavior of atoms? What was developed around and culminated around 1920 by many contributing scientists was what became now known as quantum mechanics. Now, the effects of quantum mechanics really do show up in everything on the planet, like a baseball being thrown, like a car being driven, like you or I. Except the problem is we can only really see the measurements that show that a quantum mechanical effect is occurring can only be recognized in something really tiny and light, where these effects are dramatic enough that they can be measured. So even though quantum mechanics holds for everything on the planet, we can only see the artifacts of it or the results of it by looking at its effects on things that are really tiny to see these very tiny effects that occur. Okay, so essentially, again, we could spend the entire semester talking solely about quantum mechanics, but we want to use quantum mechanics now to understand what we have learned about atoms since 1920. So the highlight of what quantum mechanics says, one of the main changes compared to classical mechanics, is that now if we envision energy for a quantum mechanical system, now instead of being continuous, what we say is that energy is discrete. And being discrete energy means it's only allowed to have certain fixed values. So if I look at a hierarchy of energy, what I see in the quantum mechanical world are that what exists are energy levels. You can land on one of these stair steps, and that stair step is of a definite value for energy. Now if I go up or down in energy, I can't enter any amount or give off any amount. I have to give off a fixed amount. You come to the next level, there's nothing in between. So there are energy levels just like there are stair steps in a staircase. if I want to absorb energy, I have to absorb energy of a certain fixed amount. Now, this is why certain atoms of a given type only absorb a certain form of the electromagnetic spectrum. Others will pass right through without being absorbed. So what we're saying is, if I want to move an electron of a hydrogen atom up from where it starts to an excited state, I have to shine light that can lift that electron exactly the height of stairs of the hydrogen atom. If I want to do it for an iron atom, the stair heights are a little different, so I will need light of a little bit different energy to lift that electron up. That means I will use light of a different wavelength for an iron atom compared to what I will use for a hydrogen atom. So this is the key feature. And once again, it's also saying something about the emission. When you stimulate atoms electrically of a certain type, they want to shed that extra electricity, electrical or fire stimulated energy you gave them. They will emit energy of only a characteristic wavelength, because the going down the hill, the steps down that they take have to be of a certain energy height corresponding to a certain light wavelength. So only characteristic wavelengths of light will be emitted by stimulated atoms of a given type, because their stair steps have a certain height, and only light of that wavelength will match those particular steps in the staircase. So from here on out, we're going to focus on the energetics of electrons. This is very important in chemistry. As a matter of fact, we can pretty much say with all certainty that all processes that chemically occur due to electronic energy. It's the electrons that are moving around, being swapped, traded, shared, transferred. It's the actions of electrons in chemistry which end up causing all changes in properties and materials, changes in colors, flashes and booms and pops that are experienced, smells, all these sorts of things are occurrences that happen as electrons are being shuffled around from place to place. So it's very important that we have some sort of understanding of the electronic energy. So first, let's just go over some basic ground rules. If you have an unperturbed atom, which has no light shining on it or any electricity being pumped into it or chemical energy of some other type being pumped into it, then the electrons in that atom have three contributions to their energy. The first is them simply flying around through space, just like when a car is moving down the highway. When objects are in motion, they have energy, and the form of energy that is possessed by moving objects is known as kinetic energy. So as electrons zoom around the nucleus, we know that they are possessing some kinetic energy that is placing them in motion. Now, electrons also experience another form of energy, which is a stored form of energy, or an energy that is due to their location. That is known as potential energy. Potential energy can be converted into energy of motion at any time, but it's kind of stored in a form until it gets converted into that energy of motion. And the source of this potential energy of electrons comes in electrostatics, or the push and pull that opposite and like charges exert on one another. And as a matter of fact, electrons possess both of those forms of energy, which could be converted into motion if changed in a certain way. And electrons have potential energy of their attraction they experience to the nucleus, the positive charges in the nucleus. Electrons also have repulsions to other electrons. So then, again, the sum of the three different types of energy that electrons can possess, again, not being stimulated from the external source of a light or anything like that. They are energy of motion flying around, energy of attraction to the nucleus, and energy of repulsion from other electrons. So let's now, as we say in the middle there, take an electron separated from a proton to infinity. Then there is no attraction between them as they are separated to infinity. But now let's start bringing them closer and closer to each other. This is a preferred situation for the electron. So it's something that the electron likes as you move the electron towards the proton or towards the nucleus away from infinity. So as an electron approaches a proton, the energy scale is defined such that this attraction that they feel on each other lowers the energy of this system. So if they were at zero energy when they're separated at infinity, as you begin to move electrons towards a nucleus, it lowers the energy of the electron so that as they become bound to the nucleus, it is a negative energy. The closer the electron gets to the nucleus, the lower its energy. And what we mean by that is the more negative the energy it experiences, the closer it gets in towards the nucleus. So when you get a bigger and bigger negative number, you're getting a lower and lower energy, as a matter of fact. Let's say something about the electronic energy levels. Now remember, what we're going to now do is assume that electrons are governed by this new science known as quantum mechanics. And since their energy is quantized, as we say, the energy is not continuous for the electrons. The energy comes in levels. So the electrons can fit onto an energy level, and then if you increase their energy, they have to go up by a fixed amount to land onto the next energy level. So if you are closest to the nucleus, you are in your lowest energy state, your most negative energy value, then you are on low rungs of the ladder. As electrons go to higher energy states, they will be on higher rungs of the ladder. Now we can see that if light impinges on it that the electron likes, it can absorb that light and land on a higher stair level. And when it does so, only a particular wavelength of light has the energy to lift the electron from one stair level to a higher stair level. So in quantum mechanics, there will be electronic energy levels. There will not be a continuous ramp of energy that the electrons can possess. So mathematically, when we analyze this, the locations of the hydrogen electrons, the electrons in the hydrogen atom, so if we look mathematically at hydrogen, we can do it very, very carefully with the mathematics of quantum mechanics. We can, as a matter of fact, solve the hydrogen atom exactly using mathematical tools. And from the results of the hydrogen atom, we get ideas about the energy that electrons can possess. So what the various energy levels are then found to be they are integer amounts of the solution to a quantum mechanical equation describing the behavior of electrons. It turns out that, as you can imagine, quantum mechanics is a little bit too mathematically detailed for our level of understanding here as in freshman chemistry. You can take a higher level class at this university where we will explain quantum mechanics in its gory detail and all the mathematics that goes behind it. What we will do is just talk about the highlights, the end results of quantum mechanics. We are not going to solve any quantum mechanical equations. What it turns out, when you solve quantum mechanics, the solutions that electrons are allowed to possess turn out to behave like simple integers. It's these integers that you can kind of think of that dictate the energy level. When you get a new integer value, you are now landed on a new level. It's not a continuous number that describes the answer of quantum mechanics. That would be continuous energy levels. Only discrete fixed numbers described by separate integers are what describes the energy levels. So what we're going to do over the next several slides is talk about these energy levels in terms of the integers that fit the energy levels. So what we will say is that electrons that are occupying the exact same energy level in an atom will have the same principal quantum number. The principal quantum number is an integer which describes the discrete level of energy that the electrons that are living in that region of space must possess. So, because in quantum mechanics energy levels are discrete and not continuous, what it turns out is that when you solve these equations, quantum mechanics boils down to 4 different integer values. Well, 3 of them turn out to be integers, 1 turns out to be half integer, as we will see. So let's first talk about the 3 integer values that describe the level of energy that atoms can possess when you solve hydrogen exactly for the motion of its electron around a single proton as its nucleus. Again, there are 4 quantum numbers that describe the location of the electron, and these 4 quantum numbers are essentially energetic coordinates. They tell the location in space based on, again, solution of complex equations that we're not going to solve, but we were, again, talking about just the highlights of this mathematical technique. Okay, so the first of these integers that we will use to describe the location of an electron is known as the principal quantum number. And it turns out the principal quantum number has a symbol that is always referred to with, and that symbol is n. Lowercase n will represent for us a principal quantum number. The principal quantum number describes behavior of electrons in the atom. Now, since it's given the name principal quantum number, you should recognize that it has importance, like the principal at a high school. So the principal quantum number kind of governs what's going to go on. The principal quantum number, it turns out when you solve the mathematics of quantum mechanics, it has very simple values. It can start at 1, go to 2, go to 3, so it only takes integers, and these kind of like label the stair steps of the energy of the electrons. In theory, the principal quantum number can go from 1 to infinity. In practice, based on the electrons that go in the table, the principal quantum number actually only goes up to 7 in the periodic table because atoms' nuclei become unstable and therefore break down, so the higher energy levels can never be accessed because there's simply not enough electrons being placed onto an atom, so that you need to populate the energy levels of electrons beyond level 7. So even though in theory the energy levels can go from 1 to infinity, in practice, in actual atoms, the energy levels only go from principal quantum number 1 up to principal quantum number 7. Each of these successively labels a higher energy orbital. Now, I also want you to think about this in terms of what we talked about a moment ago on a previous slide. The energy levels are negatively rated so that the lowest energy is the most negative of these levels. So when you're going from level 1 to level 2 to level 3 to level 4, you're going up in energy, and you should think of that as going to a less negative number of energy. Remember, the closer the electron is to the nucleus, the more negative its energy. So the lower its energy, the more negative that value is. And as a matter of fact, then, the lower the N value, the lower the energy. Also, the lower the N value, the closer the electron is to the nucleus. So as N goes up, the energy of an electron goes up or becomes less negative. As N goes up, the distance of the electron from the nucleus goes up. So all electrons on level 1 have the lowest amount of energy possible, or the most negative amount of energy, and are closest to the nucleus. Electrons on level 2 are slightly higher in energy and are slightly further out from the nucleus, and so forth. Now I want to be very clear to you that I want you to know the symbol for these quantum numbers that we're describing. I want you to know the rules if you mathematically solved the equations of quantum mechanics, what these particular quantum numbers we're describing, what values they're allowed to take. Again, as I talked about earlier, because they're representing fixed numbers and not continuous numbers, integers describe these quantum numbers, not real numbers or continuous numbers. So far we've talked about the principal quantum number. Again, the principal quantum number is symbolized N. The principal quantum number starts on energy level 1 and goes up integer-wise from there. And as you go up in integer level of the quantum numbers, you will increase the energy that electrons possess that are on that level, just like climbing a staircase. And as you go up in principal quantum number, the energy of the electron on that level increases. Now remember, that means the energy becomes less negative. That's an increase when you become a smaller negative number. And also, the distance of electrons from the nucleus increases as you go up in principal quantum number. Another important physical quantity that electrons possess as they are moving around the nucleus is angular momentum. First, let's describe what is known as linear momentum. If a particle or an object is moving in a straight line, and the object has mass m, and it is moving with velocity v, then the linear or momentum in a straight line that object possesses is a simple product of its mass times velocity. And of course, this quantity can be transferred from one object to another, just like energy can be transferred from one object to another. So objects, say like a mosquito and a truck, both moving at 60 miles an hour, if the mosquito and truck slam into you, of course the mosquito, due to its very low mass, is not going to impart much momentum. You might even not know it, but the truck will do catastrophic transfer of momentum to you. Well, electrons are not moving in straight lines. Electrons are moving, as at least according to the picture we should think of when we're using the planetary model, they're moving circularly around the nucleus. And the manifestation of momentum in a circular path is slightly different, not crazily different, but slightly different in the angular setting than it is in the linear setting. The angular momentum that an electron will possess is a product of three values. Its mass, just like linear momentum, its velocity, just like linear momentum, but also times the radius of curvature of the turn it is taking as it moves circularly around some center. So the Earth has angular momentum as it goes around the sun. A softball pitcher, an underhand softball pitcher who's twirling their arm around and around and around to release the ball is going to give linear momentum to the ball, but first generates a bunch of angular momentum by spinning the ball circularly in their hand. And so the angular momentum turns out to be a product of not only mass and velocity, but the radius by which the object is spun. So notice in that instance, if an object is moving circularly around, let's say two objects are like on a merry-go-round. If you are moving circularly, you're a distance r from the center of turning of the merry-go-round. The further out on the merry-go-round you are, the more angular momentum you possess. Now, you're moving at the same speed as the person inside of you, because, like for instance, if you're riding on a horse, they're riding on a horse, you're not getting ahead of them or behind them, but you still would have more angular momentum, and if you flew off further out from the center of curvature, you would fly off with more linear momentum as you exited as a result of the angular momentum you possess due to the radius at which you're curving. Okay, so electrons then naturally, as they get further and further from the nucleus, are going to be able to possess more amounts of angular momentum. That's going to be important as we go further forward. In instances where electrons are allowed to get further and further out from the nucleus, we're going to see that it is possible that they will have more of this angular momentum. Okay, so like energy, both linear and angular momentum cannot take any value they want. So they are not continuous. They can't be really explained using just allowing an electron spinning around an atom to have any amount of angular momentum at once. As a matter of fact, if it's not moving circularly, if it's moving linearly, it can't possess any linear momentum that it wants either. So what we saw on the previous slides was that the energy being quantized meant it only was allowed to take certain levels. The same thing is true with angular momentum of spinning electrons as they move around the nucleus. They cannot have any value of angular momentum they want. There are angular momentum levels. And again, very importantly, the further out that you get from the nucleus, the more of this angular momentum we're going to see that it is possible for you to get. So you can have bigger and bigger integers describing this curvature, if you like, if the electrons are far out from the nucleus. So if you recall from our last slide, n, the energy quantum number, says not only something about the energy, it says something about how far out you are. Well, the further out you are, the more of this angular momentum you can also possess. So in some way, what we're going to see is that the angular momentum is tied to how far out the electron is from the center of curvature in the nucleus. All right, so we are going to now introduce what quantum mechanics says are the allowed values of angular momentum that an electron can possess as it circularly moves around the nucleus. As we talked about on the last slide, angular momentum is quantized. It comes in only allowed values. It can't take any value that it wants. So there is a staircase of angular momentum, just like there's a staircase of energy. So it turns out then, like energy, an integer will govern the amount of angular momentum allowed. And this angular momentum, which is calculated in physics as a capital L, they use for the quantum number a little script L. So you see the little script L that I put there, I hope, if my fonts are coming out correctly. This will be the symbolic representation of the angular momentum quantum number. So it is only allowed to take integer values, and according to quantum mechanics, it has a relationship to the principal quantum number n. Now, as we talked about in a previous discussion a few slides back, n, the principal quantum number, dictates the energy of the electron, but also dictates, in relation to the energy, how far away the electron is from the nucleus. The higher the n value, the higher in energy an electron is, actually meaning the less negative in energy an electron is. And that means that electron resides further and further out from the nucleus. Bigger n, further from nucleus. Further from nucleus, bigger r of the angular momentum, which is m times v times r. So if you are further from the nucleus as an electron, you can possibly have higher values of angular momentum. Now you can still have low values, but you're now, because of your distance out, allowed to have higher values of angular momentum. So if, again, you solve the complex equations of quantum mechanics, which we are not going to do, we are just showing the results, and we're showing the integer results for what is allowed for angular momentum values for an electron zooming around circularly around the nucleus. Again, it's symbolized by L, and L can begin at 0. What this is saying is that in certain instances, electrons will possess 0 angular momentum. Then they can have 1 unit of angular momentum, 2, 3, 4, and it can have more and more angular momentum the further out it gets from the nucleus. So the maximum that it's allowed is in some way a function of how far from the nucleus each electron is. So it's a function in some way of n. So it turns out then, when you solve these equations, that the angular momentum quantum number governing the amount of angular momentum you can possess starts at 0 and goes up integerally from there to level 1, to level 2, to level 3. But in order to not get too much angular momentum, it's capped at n minus 1. The amount of angular momentum is always less than the principal quantum number. So what that ends up being, and we'll on the next slide investigate the connection between how many values of angular momentum you're allowed to possess on a given energy level. Now, but before we do that, I want to also point out to you that more familiarly, we do not always use number designations for the amount of angular momentum an electron possesses. We use letter designations. I want you to know these values for these letters as well as the values that I show there for numbers. Now remember, L is capped depending on your energy level, and we'll see how that plays out in our next slide. But when you have an L value of 0, that is also often called S. If you have an L value of 1, that is called P. If you have an L value of 2, you are an electron with angular momentum that is also known as a d electron. If you have L equal to 3, you are an electron having angular momentum that is called also an F electron. So the first 4 allowed values of angular momentum, 0, 1, 2, and 3, are characterized as S angular momentum, P angular momentum, D angular momentum, or F. Now you might wonder where these weird designations S, P, D, F, why didn't they just start A, B, C, D? Because you will notice when you get above F, then you just simply go alphabetically. Again, F represents 3 units of angular momentum, G is 4, H is 5, I is 6, And then notice we skip J. I want you to know that as well. You can bet somewhere on your test, I will be asking you something to do with that. So notice that the letter designation of angular momentum 6 and then to 7, they are going alphabetically from 4 up, but the letter J is skipped. And the reason it is skipped is that it was reserved for some other quantity, actually some combination of angular momentum. So we skip it in the orbital designation of angular momentum. So again, please remember, they go weirdly SPDF for the first 4, and then they go alphabetically from there. And so you should be able to tell that an F orbital has 4, L equal 3, yes, but you should also know that an I orbital, by fooling around with the numbers, has angular momentum integer 6 and so forth. You should be able to figure those sorts of things out. And you should also remember J is left out. Now, let me say just a little bit about why they did not start alphabetically at A, B, C, and D. They went S, P, D, and F. They did this historically from what they found later to be the connections to the amount of angular momentum that electrons possessed compared to what they were seeing spectroscopically. When they did an emission spectrum, which means they heated up atoms with a lot of energy and they began to glow and give off light. And they gave off light that they could spread out in a prism and make into individual lines of the spectrum that were transitions as the electrons, again, cascaded from high energy to low energy states and fell into from a high energy position to a low energy position. They characterized the appearance of these lines. Some of them were very sharp, meaning they looked very focused when the light was falling from the higher level to that level. So these ended up being called S lines because they were very sharp appearing. And because they were very sharp appearing, they later were recognized as coming from orbitals of this angular momentum characteristic. So they became called S orbitals, where the electrons possess that amount of angular momentum. The angular momentum 2, when it was later examined, the lines that were formed in this emission spectrum were later known to come from angular momentum 1 energy levels, that the lines appeared to be the primary lines, which you can interpret to mean they were the brightest looking lines in the spectrum. So the primary lines later were found to come from electrons emitting energy in orbital angular momentum 1. And so those were the p orbital lines. Then there was a set of lines that looked spread out and not so focused. They were diffuse. So they were the d orbital lines of unit 2 angular momentum. And then there was ones of lowest energy. And when we talk in terms of waves and wave patterns and the energy of waves, like from a flute or from any instrument, the ones of lowest frequency are called the fundamental lines. So the fundamental was the orbital angular momentum 3 designations, and the fundamental word became known as an electron in an F orbital.